basically today we're going to do a revision of, we're going to see the connection between combinatorics and binomial theorem. We're going to look at this formula again and prove it in a different way. Prove in a different way. And in a more interesting way as well. Different way. Okay, so firstly, we're going to prove this formula. And remember this expansion from the Pascal's triangle. Okay, so let's look at it in a different way using the counting techniques. So we're going to consider the case where x equal to 3, where if you expand it, you get 3c0, 3c1, 3c2, 3c3. Why is it connected to the number way of selecting things? Okay, so what we do is this. So we're going to expand this. So write 1 plus x cubed, you get 3 of these. In order to see the selection, we're going to color the 1s and the x. So the first bracket are the blue, the second bracket are the red, the third bracket is the green. So we can see the distinguish between them. So as you expand them, what you do is this. So you're going to do, the first way is 1 times 1 times 1, right? That's the constant term. Okay. Next, we're going to plus. We can do 1, let me see, 1 times 1 times x, right? So each of the color can only appear once in a term. It can also be like this. It can be 1, actually that should be a plus, 1 times x times the green one, right? Or it can be 1, actually not 1 anymore, Control Z. It could be, let me think, so it should be the blue one, the red, and the green, right? Now, why is that important? Because this is like one way of selecting, nothing, no x's. So 3c0 of select no x. That's why 3c0, which is 1. There's 3 of these, which is 3x, which is exactly 3c1 ways of selecting the x's. It could be from this bracket, or this bracket, and exactly 3c1 ways of doing so. And then we can continue with this idea, plus it could be, now we have 2 x's, so blue 1 and x from the red, x from the green, right? What's the other way? It could be x from the blue, 1 red, and x from the green. Or it could be x from the blue, x from the red, and then 1. Again, there are 3 ways, isn't it? Which is 3x squared. And why there's 3? Because there are 3c2 ways of selecting the 2 x's, right? So 3c2 ways of selecting 2 x's. So that's why 3c2. Okay, so it makes sense how it works. And finally, we got one way of selecting all 3 x's. So you get x here, x there, and x there. And there's only one way, x cubed, which is 3c3, which is one way, x cubed. Okay, so you can see the binomial theorem in a different way, and it makes more sense to think of it in terms of the number of selection for each x terms. Yep. Okay, good. All right, so that gives you another way to look at it and see why it's just selection. It's just not a coincidence why it doesn't match with the Pascal's triangle. This is a more interesting way of seeing the expansion. Okay, so hopefully you got something there. And then we're going to look at even more interesting stuff. And we've got 2 more properties we're going to prove. Okay, write it down. Of course, it works for x cubed. It also works for any power. You can imagine that. We just looked at this in terms of combination. We're also going to prove these 2 using similar techniques. Okay. All right. So we're going to go to the next page. And in fact, any binomial theorem formula can be explained in terms of counting. Okay. It's just a matter of how you're going to think of it. Okay, good. All right, let's look at the next formula. The proof of this. Hopefully you know how to prove it. Let's prove it again. So to prove this, what you need to do is to just substitute x equal to 1 onto both sides. Right? So let me see. I just got the recording. Okay, good. So how does it work? You get 1 plus 1 to the power n equal to nc0 plus nc1 times 1 plus nc2 times 1 squared plus dot 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 plus ncn 1 to the power n. And if you simplify that, you get 2 to the power n equal to this, which is a very, very standard proof that you can get in examination. It's very easy mark to get in the exam. This is what you have to do. And in fact, in the exam, you have to do these steps to do it, okay? You have to use this method. There is other method, but you should use this method only, okay? That will make sure you get the full marks. Okay. And then we're going to consider the case where n equal to 3 again, okay? We're going to prove this formula in a different way, okay? So we're going to prove this using combination, the number way of selecting things. Okay, good. So what we do is we're going to tell a interesting story. So we're going to select a person. So someone's going to be hosting a party. So we're going to select Ian because he's really smart. Okay, Ian will be hosting a party. He wants to invite some classmates to his house. Invitation letters were sent to 3 people. So we're going to randomly selecting 3 people. So maybe we're going to select Megan. Hopefully I spelled your name right. Is that 2 year or 1 year? 1 year? How do you spell? I'm always have difficulty spelling your name. How do you spell? It was correct. Okay, good. All right. Yeah. Okay, good. All right. Okay, good. All right, let's pick another person. Maybe pick L. And then let's pick one more. Let's pick Dora. Okay, select 3 people to come to the home. Okay, so that was really random because the first letter makes the word MED, so which is good. All right, let's list the possible outcome for this event. What's the total number of outcomes? We're going to solve this problem in 2 different ways. So who can tell me what are the possible possibilities when the letters were sent? So what are the possibilities? So how many people can come to his house? Who can come to his house? Well, what are the possibilities? Well, one possibility is that no one go, right? No one go. No one go. Okay, all right, good. That's one possibility. What's another possibility? One person go, but who could go? It could be Megan go, or Elle go, or Dora go, right? And how many ways are there? There's 3 ways. 3 ways. And how about, what's the other ways? What's the other possibilities? 2 people will go. So what are the possibilities? So it could be Megan and Elle, or Megan and Dora, or Elle and Dora. Again, there are 3 ways. And what's the last possibilities? Everyone goes, right? So all go, which is 1 way. This is 1 way, okay? Now, let's look at it in terms of selection. What's no one go means? Means 3C0, isn't it? How about 1 person go, 3C1? How about 2 people go, 3C2? How about everyone go, 3C3? And if we add them all together, why does it become 2 to the power 3? We'll see that in a minute. 3C1 plus 3C2 plus 3C3. Why would it be equal to 2 to the power 3? So this is one way of looking at the problem. The other way to look at the problem is actually asking each person. So when you ask Megan, what could she say? She could either say yes or no. So 2 ways. And if you ask Elle, what could she say? She could either say yes or no. Again, 2 ways. And if you ask Dora, how many ways? Yes or no. And how many ways are there? 8 ways, isn't it? Because it's 2 times 2 times 2, which is 2 cubed. This is a much interesting way of looking at this formula, isn't it? If you try to explain that to people in the street, they will understand you. But if you try to expand a binomial expansion and substitute 1, they will have no idea. Okay, so that's a very interesting way of looking at it. But of course, this is not a way to prove it in exam, but this is a very interesting way to see how this formula works. And in fact, that will actually help you to remember the formula. It's very interesting, and it works for 4 people, 5 people, any number of people, isn't it? Because if you can imagine with 3 people, you can imagine that with any number of people. Okay? All right, good. Excellent. All right, let's move on to another proof. Next one's not very interesting, okay, because it doesn't have Ian in it. So we're going to select 4 people again. All right. Okay, refer to the Pascal's triangle. So remember this rule. Where does that come from? It's come from the Pascal's triangle. So if I write NC0, NC1, NC2, somewhere along the line you get NCK, NCN. Right, and on the top you get n-1c0, n-1c1, n-1c2, and somewhere above will be n-1ck. Before that is n-1ck-1. Okay, and somewhere before is n-1, n-1. Okay, so basically we learned that from Pascal's triangle. If you add the 2 terms above, it gives you this term, isn't it? That's where that comes from. The addition property of the Pascal's triangle. Pascal's triangle. Okay, good. So we got that. And what else are there? We're now going to we're not going to prove it for n. We're going to prove it for a specific case like n equal to 4, k equal to 2, so it can involve people in it. So consider the case where n equal to 4, k equal to 2. The formula will become 4c2 is equal to 3c3 plus, no, not 3c3, 3c1 plus 3c2. Right, 3c1 plus 3c2 equals 4c2. And again, why is it equal? Again, you can make up an interesting story about it. Okay, there are 4 students. So who want to volunteer? All right, Alia, good. Next person. William, good. Jessica. And Richie, okay. Okay, excellent. So we'll now have all different letters, A, W, J, R. That's good. All right, so the math teachers are going to ask 2 students to help him carry the textbooks to his classroom. How many different ways can he select the 2 helpers? Well, obviously, it's going to be 4C2 ways, isn't it, to select the 2 helpers. So we only have 4 to choose from. There's 4C2 of selecting 2 helpers. That's one way of looking at it. The second way to look at it is, let's select a person. Let's say we select Alia. So in all the selections, Alia could be selected or Alia not selected. Let's look at how many ways if Alia is selected. If Alia is selected, what will happen? You only have 3 people to choose from, isn't it? So it will be 3C1 because you've already selected Alia. What if Alia is not selected? You still have 3 people to choose from, but you have to choose 2 people. Now it looks so obvious, isn't it? And so easy to remember. And yeah, okay. So does that make sense? So in all your selection, either Alia is selected or Alia is not selected, and that's the total number of ways of selecting everyone. Selecting 2 people from 4 people. Okay, that's cool. So we interpret the formula in a very interesting way. Okay, now we're going to look at some HSC questions. All right. Okay, let's look at this question from the HSC. How many arrangements of the letters of the word Olympic are possible if the C and L are together in any order? Okay, first make sure that all letters are unique. It is Olympic, no repetition of letters. And then, so therefore, how many ways? And then you have to make sure C and L are together. So what would you do? 1, 2, 3, 4, 5, 6, 7. 7 letters, but you have these 2 has to be together. What do you do? So 7 letters, so that means it will be 6 groups, right? Because they are together and times by what? 2 or 2 factorial. So therefore the answer is B. Okay, easy enough. Try the next one. Okay, good, excellent. All right, how about the next one? Who want to volunteer to tell me? These are not very hard. Maybe Marco. 2012. But then it has to be exactly 3 men and 4 women from this group. Yeah. That's it, good. All right. And of course, in the exam, you work out what that equal to, but we just can't be bothered. You would do that in the exam. I think they will still give you full mark if you write that, I think. Okay, anyway, next question. This one is a little bit more tricky. Barbara and John and 6 other people go through a doorway, 1 at a time. In how many ways can the 8 people go through the doorway? If John goes through the doorway after Barbara and no one in between. So you can think of John and Barbara as stuck together. Give a minute or so, I will ask the student to give me the answer. All right, have a try. So we've been doing a lot of problems where things go together. So that's pretty easy. So hi, anyone want to volunteer before I ask someone? Okay, I'm going to select 7 factorial. Yes, because 2 are together, but then you make sure John goes after Barbara, so you can't times it by 2. Yeah. So basically there's 7 groups with John and Barbara together. John, Barbara together. Okay, good. 7 factorial. Excellent. How about the next question? This one a little bit tricky. And by the way, this is 1 mark. And this also 1 mark. Yeah, that 1 mark tells you a lot because you know you don't have to do a lot of things. So this one a bit tricky where it's not necessarily no one in between them. But John has to go through after Barbara. So it could be 1 person between them or any number of people between them. You may do it by cases, you may do it by any technique to get the mark. All right, who want to volunteer? Give you a couple minutes to think about. Yeah. Excellent. Yeah, because all the possibilities, these are the John after B or B after John, and they are all both equally likely, isn't it? Equally likely. So therefore, it's actually 8 factorial divided by 2. Yep. Okay. Now this. Yep. Yeah, you could call it 2 factorial, the same thing, but there's only 2 ways. 3 people. It's a bit hard for 3 people because 3 people, it's not really 2 ways, isn't it? Because it's like 3 way. If it's 3 people, it's not. That's a very hard problem. I haven't thought about it. That could be the next HSC question, but I don't know. Yeah, I don't think they will ask such a complicated question in extension 1, possibly in extension 2. Okay, all right. So now I just want to draw your attention to, in fact, we actually solved this problem before on page about the pencil problem we did at the last minute. So if you go to the pencil problem, what's the pencil problem? No pencil, no pencil, where's the pencil? I forgot where the pencil is. If someone can find out where the pencil problem we did together, not here. So I think we did that problem, very similar problem before. Let me see if I could find it. There's combination. There's the saw, tomato, no, arrangement in a circle. Must be before then. Okay, yeah, so if you go to page 13, so go to page 13, it's exactly the same. E precedes letter I. Remember we did that problem together? On page 13, it's very similar to example 32. So I'm going to write a reference. So similar to example 32 on page 13. Okay? All right, good. Now we're going to do a slightly harder question. We're going to do one more HSC question. All right, let's go to the last page 32, page 30. Okay, good. Let's go through this one. The binomial theorem states this is true. Show that this is true. So basically, whenever you see sigma, make sure you write it without sigma. So that's what you look like. So what do you do? For 1 mark, you just have to substitute x equal to 1, rather than tell that interesting story. n0 plus n1 plus n3 plus dot dot dot. And n, actually make sure you put some powers down just because you're showing. So to show things you have to, I think I missed a number. Okay, good. So you do that and then you write 2 to the power n equal to this. So you have to show your steps, how you show the formula to be true. Okay? Right, that's 1 mark. Binomial theorem. Alright, good. How about the next question? Also easy mark, hence or otherwise find the value of this. So obviously you substitute n equal to 100. So if you substitute n equal to 100, that will be 2 to the power of 100. Of course, you don't need to work it out. It will be a very choose number. And then the next one. Next one, we have to do some work. You don't get this one. So this is the one above.
Yeah, like where you go after that point.
You substitute 1 onto both sides, so 1 plus 1 to the power n, and when you substitute 1, all the 1 disappears. You just have the binomial coefficients left.
And then count it.
Yeah, because that's why it gets confusing. So every time you see a sigma, just rewrite it. So 0 into k, you get 0. 1 into k into 1. N into k, you get n. So you get this series.
Right.
Yeah.
The last line of it, if I wrote that.
I'm not sure. You have to, because he asks you to show. Because when they say show, you got to show this. I mean part 2, part 1. Yeah, you have to show 1 plus 1. You can't just go this because you're just rewriting the whole question. They will not give you mark.
I still get how the last line.
How the last line? Because this line shows this. This is just a formula written without the sigma notation. You don't have to rewrite it in sigma. But you just have to know that sigma stands for this. That's why I wrote it here. It's showing these formulas to be true. So it's saying this. Let me give you an easy example. Let's say we got this k equal to 1 to n equal to n plus 1 and like this formula, right? So you just have to asking to show this is just the sum of the first n numbers. Get the idea? I'm just rewriting the question. It's not showing that how you interpret the sigma. It's asking to show this formula. But they're just a bit lazy. They don't want to write all the terms. They just write it in one term. Does that make sense? It's proving this. Basically, they want you to prove this formula. They want you to prove this. Prove. But they're not going to write this. They're just going to write it in this closed form. They just want you to do some work and understand what that formula is. So they want you to prove this. And how do we prove it? We substitute x equal to 1 onto both sides. Yeah, so does that make sense? So it's not asking you what that means. It's asking you to prove this formula. But they just condensed it in this closed form, in a shorthand notation. Does that make sense, Alia? Yeah, okay. Yeah. Okay, good. All right, next question again. They want to prove it. So again, they didn't write it in the full ways. So you have to do some work. Just rewrite the question. I'm just rewriting the question. Rewrite question. Okay, so your first step is to rewrite the question to be put 1 there, you get n1, 2 n2, 3 n3, all the way to n n n, like that. Okay, so rewrite the question and hopefully remember how it works. In this case, you're not actually substituting a number first. You have to do something first. What would you do first? Well, first write down the expansion first, and then decide what to do. So what would you do? All right, what would you do first when you see these consecutive numbers, 2, 3, everything? What would you do? You have to differentiate. So differentiate both sides. Both sides. Okay, good. So what you do is, if you differentiate both sides, you get n, 1 plus x power n minus 1. And you also differentiate the right. Keep in mind this is a constant, so you get 0. Plus n1 plus 2 n2x plus 3 n3x squared plus dot 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 n x power of n minus 1. Run out of space. Okay, good. So once we do that, yep. And then what you do is, then you substitute x equal to 1. Okay. Substitute x into 1, you get n 2 to the power n minus 1. You get n1 plus 2 n2 plus 3 n3 plus dot 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 n. Okay. So that's what you do. All right, proven. That's a very standard proof. We did that before in the examples. Right. And then we'll do some question about permutation that relates to this formula. All right, all good. Let's move on. I think we have enough time. You've seen it before. Okay, good. Next problem is the same question from the same paper. A box contains n identical red balls, n identical blue balls. A selection of R balls is made from the box. Explain why the number of color combinations are plus 1. Okay, think about it. Let's see how that works. So you got blue and red. That's good. So you draw a table. Actually, I do in black. Draw a table. Okay, so we got this. We could have blue here, red here, right? So what are the possibilities? You could have no red balls, R number of blue balls, right? Because you select R balls altogether, R balls. Or you could have one red ball, R minus 1 blue balls. Or you could have 2 red balls, R minus 2 red balls, blue balls. All the way to R red balls, no blue balls. So how many ways altogether? Well, you can see there's R ways, and there's 1 way. So altogether there is R plus 1 ways. But you say explain, so you use a table. and then maybe write some sentence if you can. If not, just to explain what your table means. Maybe you can write, you have 0 red balls are blue balls. And you just have sort of just write some words, and then 1 red balls. I don't know, just rewriting the table. R minus 1 blue balls. I think the table is very clear. You just have to explain or show for 1 mark. Okay? Alright, good. Let's do the next part. The next part, there are white balls, but the white balls are different. They are labeled consecutively from 1 to n, and you're going to select n minus r balls. Okay? And explain why this is the number of selections. Again, only 1 mark, so what would you do? Well, that's pretty easy. The balls are different. You just go n, c, n minus r, isn't it? Right? That's the number of ways of selecting the n minus r white balls. But we'll know by symmetrical property that this must equal to nr. You probably have to mention the word symmetrical properties. Yes. Okay, good. So, but you have to write this first before you get to that. Okay, you have to show the connection. All right, that's for 1 mark, and the last part gets a bit harder. And we'll try to solve it. And if you run out of space, go to the next page. There's a lot of blank space on the next page. Okay, so let's go to part 3. So basically, we're going to find how many ways of selecting. So there's n red balls, n blue balls, and white balls, which is labeled, all placed in 1 box. And a selection of n balls is made using part B, or otherwise show the number of selection is this. Okay. All right, so what we do is this. So when we're going to select n balls, we're going to divide into cases. The first case is, okay, let me think. You will have 0 red and blue balls and n white. Actually, let's do it in a table. That will be easier. So we're going to draw a table. So this is the white, this is the red and blue, right? So you could have no red and blue balls and white balls, okay? And when that happens, the number of ways that could occur will be NC0. Yes, NC0 because, how does it work? If R is 0, then and yeah, NC0. Okay, good. And that will have 1 way. Is it 1 way of selecting no red and white balls? Okay, good. You could have 1 red and blue and n minus 1 white. So in that case, will be n1 ways of choosing the white. And this will have 2 ways. Now, why is there 2 ways? Now, that's in part 1, right? If I select R balls, there's always R plus 1 selections, right? So if R is 1, there's 2 ways. 2 ways, right? If R is 1, there's 2 ways. So there's R plus 1 ways. Okay, so let's keep going. You could have 2 red or blue balls. There will be 3 ways. In that case, will be n minus 2 white balls and C 2 ways. And then all the way to n red and blue balls, n plus 1 ways, and that will be n ways. 0 white balls. Okay, something like this. So to get the total number of ways, you get a series because you go 1, so the total ways will be equals to 1 times n0 plus 2 times n1 plus and do 1 more. 3 times n2 plus n plus 1 times nn. That's the total number of ways. And you have to use part B to sum that series. We'll look at part B in a minute. Now, what does the part B tell us? Part B tells us two formulas. There's this formula, which is n0 plus n1, n2 plus dot dot dot, nn. And that's the other formula is n2 n minus 1 equals to n1 2n2 plus dot 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 n n. Now, neither of these looks like the one above. So what do? You can, if you look at more carefully, you have to combine them, isn't it? So how do we combine them? Maybe we can. Now, if you look at the coefficient, this is 2 times n1, but there's no 2 in front. This is 3 times n2, but n2 has a 2 next to it. So what would you do? You're going to add them. So if you add these two, you get a 3. If you add these two, you get a 2. Okay? So we're going to add them, and we'll get a sum for that series. So we're going to plus the two series together. So we can do that on the next page. So next page, there should be some space, a lot of blank space on the next page. You can write on the last page. So we're going to add these two series. So what I'm going to do is to maybe highlight it and add them. Control C, and we'll go to the next page. All right, Control V. Cool. Okay, so we're going to add them together. So how do we add them? It's pretty simple. So we're going to do, let's add them. So we get n 2 to the power n minus 1 plus 2 to the power n equal n0. Remember, these two become 2 lots of n1, 3 lots of n2, plus dot dot dot. That will be n plus 1, because there's an n, there's a 1, and n. Right? This is what we want. This is the total number of ways, isn't it? And then we have to simplify this. If we simplify the left side, you can write that as 2 lots of 2 to the power n minus 1. All right, so we're not going to copy, and you can factorize it out. That will be this. I think that's all you have to do. Okay, so what's that? Yeah, I think I proved it. Okay, so therefore this is the number of selections. Number of selections. All right, hopefully that makes sense. If not, you can ask more questions. I think that we've finished the booklet. Next lesson we'll maybe do binomial probability. Okay, all right. So today I'll give you some past papers to do, and then we'll finish done.